We are on exponential functions. Our learning targets: solve exponential equations using the same base, graph exponential equations, determine if an exponential function is a decay or growth graph, and write an exponential equation given its graph. So what exactly is an exponential function? It's a function where the variable x is in the exponent. That's the power. So some examples here are f of x equals 2 to the x, or y equals 2 to the x. Notice the x is up there as the power, or the exponent. F of x there is equal to 5 to the x minus 2. So other things can be up there with the x and the exponent as well. So it can be a multiplication thing, a subtraction, an addition. So whatever is up there, as long as x is in the exponent up there. An exponential function is a function of the form f of x equals b to the x, or y equals b to the x. B is referred to as the base, and it's a positive real number other than 1. So b is greater than 0 but not equal to 1. The domain of an exponential function is all real numbers. So x can be any real number. And then we always write that out like this: parentheses, negative infinity, comma, infinity, parentheses. So let's go ahead and graph some exponential functions. So we've got f of x there equals 2 to the x. You can either do this by hand and just take each time and take the values that are there in the t-table there and plug them in for x. So in other words, I could do 2 to the negative 2, plug that into my calculator and get my answer. 2 to the negative 1 equals, plug that in my calculator. 2 to the 0 equals, 2 to the 1 equals, and 2 to the 2 equals. So let's just go ahead and do that way. So I'm going to pull up my calculator and just plug them in there. Maybe I'll just do a few of them. So 2, caret key, negative 2, enter. I get 0.25. 2, caret key, negative 1, enter. I get 0.5, and so on and so forth. So let me put those in here. So 0.25, 0.5, 2 to the 0 is 1, 2 to the 1 is 2, and 2 to the second there is 4. So I'm going to plug them up here in my table. And now I'm just going to plot them. So I'm going to go over to negative 2 and then up 0.25. And then over to negative 1 and up a half. And then 0, 1, 1, 2, and 2, 4. Connect my points, and there's my nice graph. So you can see as I go from left to right on the graph there, that my graph is going up. So this is considered an exponential growth graph. So now let's graph out the other one here, y equals 1/2 to the x. So we can do the same thing. We can plug this into our calculator. So I'll do a couple more of these again with you. So I'm going to bring up my calculator here. And I'm going to go ahead and plug these values in here. I'm going to do parentheses 1 divided by 2, caret key, negative 2 equals. I can do parentheses 1 divided by 2, parentheses, caret key, negative 1. So, and you keep doing that for every single one of your values. So let me put them in up here. So I'm going to put them in the table as well. And then let's go ahead and plot those. So again, we plotted those out and connected our dots. So then what kind of graph is that as I go from left to right on the graph there? You start up on the left, and then it just, as I go to the right, the graph there goes down. So that's called a decay graph. All right, so let's move on over here and kind of do some explanation here of growth and decay graphs. If you want, you can just plot these into your graphing calculator each time and see if they go down or if they go up. So if I did that, I could come over here to my graphing calculator, clear all this out of here, go to my y equals. I could plug in like 5 divided by 2 parentheses caret key x, hit the graph button. It will graph up my points there, and as I go from left to right there on the graph, I can see that it goes up. It starts down and then it goes up as I go from left to right on the graph. So that's considered a growth graph because it's going up over time. Okay, so we already did f of x equals 2 to the x, and that was a growth graph. F of x equals 5/2 to the x, we just plotted that up. It also goes up. If we were to do f of x equals 15 to the x, that would also be considered a growth graph. And why is that? Well, up there in the key concept box there, it says if b is greater than 1, which they all are, 2, 2.5, and 15, those values are all greater than 1, so those all represent exponential growths. Then the second line up there in the key concept, it says if b is somewhere between 0 and 1, then they're decay graphs. Well, we saw that f of x equals 1/2 to the x. 1/2 is a value in between 0 and 1 because it's 0.5, and 0.5 is somewhere between 0 and 1. So that was considered an exponential decay. So let's also graph out this 3/4 to the x and see what that looks like. So if I go to my y equals here, I clear out what's in there. I do parentheses 3 divided by 4, parentheses caret key x, and hit graph. I can see that my graph there is going down over time, so that's considered a decay graph. All right, so if your b value is somewhere between 0 and 1, it is considered a decay. If your b value is greater than 1, that's considered a growth graph. So let's determine whether each function represents an exponential growth or decay. So we just did 5 divided by 2, that's actually 2.5, and 2.5, the b value is greater than 1. And so since b is greater than 1, it's considered a growth graph. The other thing you could do is plot it out in your graphing calculator. 3/4, we just plotted that one out as well, and we could see that was decay if we plotted out on our graphing calculator. But you can also just look at 3/4. 3/4 is 0.75, and that's a value somewhere between 0 and 1. And so that's considered a decay graph. Again, you could graph out y equals 15 to the x, b is greater than 1. So it's considered a growth graph. Then our other one here is our b value there is 2/3, which is 0.666666, and that is a value somewhere between 0 and 1. So that is considered a decay graph as well. Again, you could have plotted that out on your graphing calculator as well. So now we're supposed to graph these two exponential functions and then state its domain and range. So if we wanted to, we can either go ahead and just do these by hand. So if I were to do that, I could totally do that. I could just go ahead and put those into my graphing calculator there, get my solutions there, and then plot, and then go ahead and put them in the table and then plot those out. So let's go ahead and let's do that. So I'll just do a couple of those just to show you how to enter it in. So I'm going to get out of this, I can quit. I'm going to plug in 3 parentheses 4 parentheses caret key -2. Enter. And it tells me it's 0.1875. If I do the next one here, three parentheses 4, just doing exactly what it says in the function itself, and then where the x is, I'm going to put the value of -1 in there, and I get 0.75. And you could keep doing that for each one of those, and I'm just going to fill in those values now. 3, 12, and 48. So 0.1875, 0.75, 3, 12, and 48. Obviously, you know, when you do the 2, you're not going to be able to literally put 48 on there. It's too big. So we'll just do the first 4 there. So -0.2 and about 0.1875. -1 and 0.75. 0.3. 112. And then connect your points. All right, and then we'll come back and do the domain and range. Let's go ahead and graph the other one as well. So let's put those into our graphing calculator there. So two parentheses 1 divided by 3 caret key -2. We get 18. 2 parentheses 1 divided by 3 parentheses caret key -1, and we get 6. So on and so forth. So 18, 6, 2.666, and 2/9. So I can put that up here, 18, 6, 2.6 repeating, 2/9. All right, so let's plot those. So -2, 18, it's too far off my graph. -1, 6. 0, 2, 1, and then it looks like 2/3, a little less than 1, and then 2, and then a little bit down here further. So again, connect my points. So obviously that first one there is a growth graph, and the second one there is a decay graph. Again, the growth graph is based on that 4 in the first one there. It's 4 to the x, and that second one there, the decay graph is based on that 1/3. And so let's name the domain and range for each of these. The domain, it always looks left to right. So if you look to the left, that arrow to the left there is going to keep going to the left forever and ever and ever. That's -infinity. And up there at the top, or you got that arrow at the very top up there, it's going up and to the right forever and ever. That's infinity. The range you look bottom to top, so the bottom value down there, it's approaching the x-axis. It's not going to touch the x-axis, but the bottom down there is approaching the x-axis, which is 0. So we're going to do parentheses 0. And then the top there, it goes up forever and ever and ever. That's infinity. So with negative infinity and infinity, you always put parentheses around that. And because it's not including 0, we put a parentheses by the 0. Let's do the domain and range for letter B. So the domain here, it's at the, you look left to right, so at the left it's up there at the top there, so it's going up and to the left forever and ever and ever. That's negative infinity. And then over on the right there, that arrow's going to the right forever and ever and ever, so that's infinity. And remember, that's true for all exponentials, that the domain is always going to be parentheses, negative infinity, comma infinity, parentheses. The range, so look bottom to top here. So at the bottom there, we have, it's approaching 0, but not including 0. And at the top there, it keeps going up, up, up forever and ever. That's infinity. So parentheses, 0, comma infinity, parentheses. All right, so steps for solving exponential equations with the same base. Here are some steps here. We're going to determine if numbers can be written using the same base. We're going to rewrite the problem using the same base if it can't be, and then we're going to use the property of exponents to simplify the problem. And it says once the bases are the same, drop the bases and set the exponents equal to each other, and then solve the problem by isolating the variable. And then you're really good there with step 5. So let's look at this one. So what I do here is I look at the smaller number and think in terms of powers. So the smallest number here is 2. Can I take 2 to a certain power and get 8? Well, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. So if you're not good at these, just put them in your calculator and see if it's true. And we need to rewrite the 8 over there in terms of base 2, so yes. I can rewrite 8 there in terms of 2 to the third. So because that's now, see the bases now are both 2's, it's 2 to the x and it's 2 to the third, you can drop the 2's and just say the powers are equal to each other, so I can simply say x equals 3. And that's our solution. All right, so the next one, letter B there. Again, I'm going to write them in terms of the same power. So the smaller power there, the smaller number between 3 and 81 there, not looking at the exponents, just looking at the bases, the bigger numbers there. You've got 3 and you've got 81. Which number is larger, the 3 or which one's smaller, the 3 or the 81? The 3 is. Can you write 3 to a certain power to give you 81? Well, let's try. So I'm going to do 3 to the first, 3 to the second, 3 to the third, and so on and so forth. So you can see there that 3 to the fourth there does give us 81. So I'm going to rewrite that 81 as 3 to the fourth power. Okay, that's the only one that changed because the other one was already as 3 to a certain power. Now that the big numbers there, the 3's are exactly the same, I can set the powers equal to each other. I can say 2n plus 1 equals 4. And now I can just solve this like you always do. You would get n all by its 2n by itself, so you'd subtract 1. And then you got to get rid of the 2. The 2 is connected by the n by multiplication, so to get rid of the 2, we have to divide. So our n ends up being 3/2 or 1.5. All right, so now let's come down here and let's try another one here. Now this one here is a little tricky here because the smaller number is 4. But you cannot take 4 and take it to a certain power and rewrite the 8. because 4 to the first is 4 and 4 to the second is 16. So I'm going to have to find a smaller number than 4. Well, both the numbers are even, so I'm going to think in terms of 2's. Can I rewrite 4 in terms of 2? Yeah. 2 to the second there is 4, and then 2 to the third there is 8. So I'm going to rewrite 4 there as 2 to the second. So I've got 2 to the second to the 2x, and I've got 2 to the third to the x minus 1. So I can get rid of the 2's there, and then I just have left on the left-hand side here, 2 times 2x equals 3 times x minus 1. So multiply the left-hand side, distribute the 3 through over here on the right-hand side. And then I'm just going to go ahead and solve this. So I'm going to subtract 3x from both sides. And we end up there simply getting x equals negative 3. All right. Letter D there, again, you want to rewrite the larger number there in terms of the smaller number if you can. So 5, can you write 5 to a certain power there to give you 25? Yeah, 5 to the second power is 25. So since the left-hand side is a smaller number there of 5, I'm going to leave that alone for a minute here. Now, the 5 to the second is down there in the denominator, and we actually need it up at the top. To move it to the inverse side there, we have to change the sign of the power. So the sign of the power there has to be a negative. So we can flip it up, and then since it's a positive down in the denominator, we can flip it up and make it a negative 2 there. So now the 5's can go away, and we can say 2x equals negative 2. And then just solve that for x. So divide both sides by 2. And we get x equals negative 1. All right, so this is just kind of going through a few things here. You've got g of x equals 2 to the x, it's in blue. You've got h of x equals 3 to the x, it's in red. So just some things to notice about these. Exponential functions with positive bases greater than 1 have graphs that are increasing. So both, we've got 2 and 3 there. They're both increasing. They're both going up as I go from left to right there on the graph. Both of them never cross. This kind of a function, exponential functions, will not cross the x-axis. And then the x-axis ends up being the left horizontal asymptote with an increasing graph like that. So some other things here, a smaller base means that the graph rises more gradually. So the smaller base there is 2. So you can see that the blue graph is farther out. The red graph, because it's the 3 there, it's a larger base, so it's going to rise more quickly. So it's steeper or closer to the y-axis there. So the red line there on the right-hand side there, you can see that it's closer to the y-axis. The exponential functions will not have negative bases. All right, so we've got some here and they're graphed out, 2, 4, 1, 2, 0, 1. You've got h of x there is 2, 9, 1, 3, 0, 1. Just kind of looking those over there, you can see how they're graphed out. You can see that the y values there are a lot bigger than the y values for the 2 to the x. The y values for the y to the x are a lot larger values there. So that's another way that you can tell that it's going to end up being a steeper graph there. So I just wanted you to see some of those, literally just see those values being compared to each other there. So let's come over here and let's match some functions here. So some other things I'm going to note as we do this one as well. You can see that the first graph there and the third graph there are both going down over time, so they're both decay graphs. And then the middle graph there, it's going up as I go from left to right. So let's consider a growth graph. So we know that our B value for a decay graph should be somewhere between 1 and 0. And so looking at that, we know that our B value here is 1/2, and our B value over this other one here is 1/4. Both of those are somewhere between 0 and 1. So both of those are one of the decay graphs, so they're on the ends there. And then the letter C there has a B value there of 4. So since it has a 4, that's greater than 1. So we know that this has to be letter C here. All right, so now let's look at the next two here. So the decay graphs, how we can kind of compare those is let's look at the y-intercepts. So my y-intercept in this first one there is a 3. And notice what's sitting here right in the front of that graph there is a 3. And so we know that this here is letter B. Okay, and now look at the other one here, the other decay graph there. The y-intercept there is 1. It's not written in front of this other one here. Whoops, I'll move it over. One more time. Let's try that. So the one there is supposed to be right there in front of the 1/2 there. So this here ends up being the y-intercept here is a 1 there. So you can see it's not written there, but it's supposed to be a 1 value right there. And so because of that here, we can say that this is letter A. So the y-intercept tells you if there's a number out there in front of what's in the parentheses in front of the x there, that y-intercept, that is the y-intercept there, and then that value should actually be sitting out there in front. So, and then you can even look at the growth graph there too. This growth graph here has a 2 there in front, and the letter C there has a 2 out there in front. Right there. So again, the y-intercepts there are in front of the B value there. All right, so those were our learning targets, so you're working on your worksheet.